2 weeks ago we did a poll and asked you which of 4 elements you would like us to discuss. And you chose nitrogen. Now this element is number 7 in the periodic table and there is a lot to say about it. It is used for construction, farming, and it has a beautiful history. Welcome to Cube Chemistry, where we will discuss all the elements of the periodic system and also do experiments. Now if you like this video and want to see more, make sure to subscribe. Also, if you want to influence next week's element, make sure to fill in the poll. Now this cube contains nitrogen. Now like a few times before, in order to prove this, I would need to use the Tesla coil. Now it worked, but the problem was that the footage that I created wasn't up to my standards. So I decided to use the footage of Engineered Labs, which was reflecting the real glow much better than my own footage. Now as you can see, this cube is giving a nice purple glow. And that is what is telling us that we're dealing with nitrogen here. Every gas, when excited, gives out a distinct color, and this specific color correlates with nitrogen. Now both the cube and the Tesla coil come from Engineered Labs, and if you are searching for a gift or want to collect these cubes yourself, click on the link in the description. Make sure to also use the code as it will provide you with a 10% discount, and also you will be helping out our channel. Nitrogen is one of the most fascinating elements, not only due to its abundance, but also because of its essential role that it plays in life and industry. Represented by the atomic symbol N and holding atomic number 7 on the periodic table. In terms of prevalence, it ranks as the 5th most abundant element in the universe. On Earth, it makes up to roughly 78% of our atmosphere. Now this means that every breath that we take consists mostly of nitrogen, although it goes unnoticed by our bodies. Now, despite the fact that it is a really common element, it took centuries for humanity to recognize nitrogen as an independent element, primarily because it behaves differently from other gases in our atmosphere. It doesn't support combustion or sustain life, unlike oxygen, which humans depend on for survival. Now let's go back to when this element was discovered. We need to travel back again to the 18th century, a time when scientists were eagerly exploring the properties of air. Oxygen has recently been identified as a vital component of air, leaving chemists wondering what made up the remaining portion. In 1772, Scottish chemist Daniel Rutherford was studying gases as part of his doctoral research. Rutherford devised an experiment to isolate noxious air, a mysterious compound that didn't support life or combustion. He removed oxygen and carbon dioxide from a sample of air, leaving behind an inert gas, what we now call nitrogen. Now the experiments that Rutherford did were quite grim for our standards. Rutherford placed a burning candle, I'll show you what that looks like, or a small animal such as a mouse in a closed container to consume the oxygen in the air. Combustion, in the case of the candle, or respiration, in case of the animal, gradually used up the oxygen in the container. Now if Rutherford indeed used an animal for this, it was kinda mean and not very efficient, since the mouse or the other animal would have died long before all the oxygen would have been depleted. Now the experiment was designed to deplete oxygen while leaving behind other gases. Now, as you can see in the beaker that I used in this experiment, about 20% of the beaker filled up with water after the candle stopped burning. Once all the oxygen was consumed, the container also held carbon dioxide, a byproduct from combustion and respiration. Rutherford used a solution of potassium hydroxide, to absorb the carbon dioxide from the container, leaving behind only the noxious air, the component that did not support life or combustion. Now in our experiment I used sodium hydroxide, which had a similar result. Now Rutherford observed that the remaining gas could not support the burning of a candle, nor it could sustain a living organism. This gas appeared to be inert and lacked any apparent life-supporting properties. Now, based on these observations, Rutherford concluded that this gas was a distinct type of air. While he called it phlogisticated air, his findings marked the discovery of nitrogen, distinguishing it from oxygen and carbon dioxide. Now, it was noted after a while that the nitrogen gas prepared by using the Rutherford method seemed to have a different molecular weight than nitrogen gas prepared by the decomposition of nitrates. This led to the discovery of argon as a component of our atmosphere. Although Rutherford was credited with the discovery, he was not alone in his findings. Joseph Priestley, Carl Wilhelm Scheele and Henry Cavendish all studied this strange lifeless air, each adding to our understanding of its properties. Henry Cavendish's meticulous work on atmospheric composition further clarified nitrogen characteristics. Rutherford referred to the gas as phlogisticated air, based on the phlogiston theory, which posited that a substance called phlogiston was released during combustion. Over time, the phlogiston theory fell out of favor. Nitrogen became recognized as a unique element, setting the stage for future discoveries about its nature and applications. The name nitrogen itself has an interesting origin, rooted in both science and language. The term comes from the Greek words nitron and genes, meaning niter forming or producer of niter. Niter, or potassium nitrate, was an important substance in the 18th century because of its role in gunpowder production. This property influenced the French chemist Jean-Antoine Chaptal, who named the element nitrogen in 1790, emphasizing its relationship with niter and nitric acid. However, nitrogen has also another name in French, azote, derived from the Greek word azotos, meaning lifeless. This name reflects the inert properties from nitrogen, which neither support combustion or sustains life in a pure form. The dual naming convention for nitrogen and azote, remains to this day in different languages, hinting at its reactivity in compounds and its fundamental inertness as an elemental gas. In Dutch, this element has the daunting name stikstof, which can be translated as a substance that makes you suffocate. I think that name is quite appropriate, and it falls in the line with azote from the French. Nitrogen's inert properties continue to intrigue scientists after its discovery. Unlike oxygen, nitrogen doesn't react readily with other elements. The reason behind this stability is a strong triple bond that holds together the two nitrogen atoms in a nitrogen molecule, N2. This bond is one of the strongest bonds in nature, requiring a significant amount of energy to break. Like earlier mentioned, because of its inertness, nitrogen gas does not support combustion, respiration, or many other reactions under standard conditions. These characteristics make it incredibly useful in situations where chemical reactivity must be avoided. For instance, nitrogen is commonly used in packaging for food products to prevent spoilage. Additionally, nitrogen is used in laboratories to create inert environments for experiments that are sensitive to oxygen or other reactive gases. Nitrogen's stability has led to the use of a variety of industrial applications. One common example is its role as a shielding gas in welding, where an inert atmosphere is needed to prevent oxidation and contamination during the welding process. The lack of reactivity allows for cleaner and stronger welds. Nitrogen is also used in cryogenics, especially in the form of liquid nitrogen. At minus 196 degrees Celsius, liquid nitrogen is extremely cold and is often used for preserving biological samples or even culinary applications. Its quick freezing abilities make it ideal for creating smooth ice creams and other unique frozen dishes. In the petroleum industry, nitrogen gas is used to remove impurities from fuel, while in electronic manufacturing, nitrogen creates a protective atmosphere that prevents oxidation. The element's role as an inert buffer extends even to transportation, where nitrogen is used to inflate airplane tires and Formula One car tires due to its low reactivity and ability to remain stable under high pressure and temperatures. Now, this may sound strange, but nitrogen isn't just important for industry. It's also a vital element for life on Earth. It is a core component of amino acids, which are the building blocks of proteins, as well as nucleic acids like DNA and RNA, which carry the genetic blueprints in living organisms. Without nitrogen, life as we know it would not be possible. Despite its abundance in the atmosphere, nitrogen gas, N2, is not directly usable by most living organisms. The strong triple bonds that make nitrogen inert also make it difficult to break apart and utilize. Instead, nitrogen must be converted into more reactive compounds like ammonia or nitrates through the process that we know as nitrogen fixation. Now, nitrogen fixation is essential for incorporating nitrogen into biological systems. This process occurs naturally in two primary ways, through lightning and through the action of certain bacteria. When lightning strikes, it provides enough energy to break the nitrogen bonds, allowing it to combine with oxygen and form nitrogen oxides. These compounds eventually dissolve in rainwater, enriching the soil with usable nitrogen. However, the most significant source of fixed nitrogen comes from bacteria. Certain soil bacteria from plants like peas and beans can convert nitrogen from the air into ammonia. This ammonia can then be used by plants to grow and build proteins. Without these bacteria, ecosystems would struggle to obtain sufficient nitrogen for plant and animal life. Now, for its essential role in life, it should be noted that most plants must obtain this as minerals, such as ammonium salts or nitrates, from the soil, where fixation does not play a role, and that artificial fertilizers are therefore needed for intensive agriculture. Now, the process of nitrogen fixation isn't limited to nature. In the early 20th century, German chemists Fritz Haber and Karl Bosch developed the Haber-Bosch process, a method to produce ammonia from nitrogen gas and hydrogen. This breakthrough allowed for the mass production of nitrogen-based fertilizers, which revolutionized agriculture and made it possible to grow food on a large scale. Now, what is this Haber-Bosch process? Heating nitrogen and hydrogen gas with a glowing platinum grid as a catalyst, the platinum absorbs the H2, which then sits on the surface as an individual atom, significantly aiding the reaction along. However, the widespread use of synthetic fertilizers has also led to environmental challenges. Excess of nitrogen from fertilizers often leaches into waterways, causing eutrophication, which leads to algae blooms and deoxygenated dead zones. Furthermore, nitrogen fertilizers contribute to the release of nitrous oxide, a potent greenhouse gas that has a significant impact on climate change. But nitrogen is not only used for agricultural purposes. Nitrogen compounds play a crucial role in medicine and industry. One well-known example is nitrous oxide, or laughing gas, used as an anesthetic, pain reliever, in dentistry and surgery. In the chemical industry, nitrogen is a compound of nitric acid, which is used to produce fertilizers, explosives and dyes. Now, laughing gas is also misused as a party drug, sometimes even by people foolishly enough to drive. This ultimately leads to paralysis because it damages the spinal cord nerves. The explosive nature of certain nitrogen compounds has made them valuable in the production of gunpowder, TNT and other military applications. Nitrogen's ability to form both stable and reactive compounds makes it a foundational element in the production of numerous synthetic materials and compounds. Nitrogen isn't only present on Earth, it's also common throughout the universe. Observations show that nitrogen exists in the atmospheres of many celestial bodies. For instance, nitrogen is the primary compound of the atmosphere of Saturn's moon Titan, similar like on Earth. But here it makes up around 98% of the atmosphere. Now, this similarity has led scientists to study nitrogen's role in the formation of planets and potential for life beyond Earth. The presence of nitrogen on other planets and moons raises questions about how life-sustaining elements may be distributed across the galaxy, and what that could mean for finding life in places beyond our planet. Nitrogen is so abundant in the universe because it is part of the carbon-nitrogen cycle. And this is the primary form of nuclear fusion in larger and therefore hotter stars. Now, our Sun isn't like that, and we rely on a proton-proton cycle. Below you can see the rate determining. Now, this process is extremely slow because it essentially involves beta decay, which often takes years. And it must occur in the extremely brief moment when two colliding protons are in contact. The probability of this happening is exceedingly low, so almost always the protons will simply bounce off of each other, unchanged. Now, the carbon-nitrogen cycle starts with this. Now, these collisions can only occur at higher temperatures as the repulsion between a proton and carbon is 6 times greater than between a proton and a proton. However, it is almost always successful because no beta decay is needed to form this. It is simply requiring a rearrangement of already present protons and neutrons. And this can then decay at its own pace to this. And this process repeats itself several times, successfully producing below. Now, nitrogen's story is one of scientific discovery, industrial innovation, and biological necessity. From its identification by pioneering chemists to its role in modern agriculture, nitrogen has proven indispensable across nearly every domain. The journey from noxious air to critical components for life, industry, and even space exploration reflects nitrogen's unique place in both nature and technology. As we continue to explore nitrogen's applications and impacts, we are reminded of how vital this seemingly inert element truly is. Nitrogen's future potential, from sustainable agricultural to planetary exploration, keeps this element at the frontier of scientific progress. And so, the story of nitrogen continues, shaping the world we know and the worlds we have yet to discover. Now, as always, if you think I forgot something, let me know in the comments, and if you want to see more videos like this, make sure to subscribe.